This tutorial is about numerical integration using two-point Gauss quadrature, and compared to one point where we had only found one point in the interval, we find 2 points, x1 and x2, and we model the integral as the linear combination of the function values at point x1 and x2 weighted by some constant c1 and c2. And again, this would give exact result for a straight line or a parabola or a cubic equation. And using those in this equation, we can find values of c1, c2, x1, and x2, which comes out to be these. And now we can implement this in our code. Again, you just take the Gaussian quadrature for one point, and you can just modify it to make a 2-point. The only difference is that in case of just c1 and x1, now we are also finding c1 and c2, which c2 is pretty much same as c1, and then we are also computing x1 and x2 based on the equations that are derived for the 2-point method. And in this case, we also plot both the line between the 2 points as well as the stem of the 2 points, so that you can see which 2 points have been used to calculate the integral. And then we add that value for each interval into our numerical integral value. And at the end, we plot the analytical result and the numerical result to compare. So when we run this code, we see that compared to the 1 point, we get very exact, accurate result for dx is equal to 2. So clearly this is more accurate than 1 point. And if you look closely on the plot, you can see that the green points are the ones that have been chosen to find the integral within this interval. And that's why it's called open method, as I mentioned previously, that the points that are used to compute integral is not fixed to the endpoints of the interval. Rather, they are arbitrary. They are found to be the ones that provide best result for first order, second order, and third order integration, but then they can be extended to higher order integration for some expecting some errors. So that is the 2-point Gaussian quadrature method.